You're watching the Control Design Educational Video Series, Motors and Drives. This video is brought to you by our sponsors, Beckhoff and SEW-EURODRIVE. More information on our sponsors will be provided later on. You can also find company and product information provided in the information section below.
Electric motors are the largest consumers of electricity in the United States, according to the U.S. Department of Energy. In manufacturing, motors account for more than 50% of electricity consumption on machines driving fans, pumps, conveyors, compressors, grinders, and mixers. However, improper selection and maintenance of these motors can lead to inefficiencies and related costs. It's important to understand motor and drive basics to ensure they are well suited for the applications. For a custom machine builder or OEM, it is usually a good practice to consider the cost. However, the application, operation, and environment are the big players in motor selection. It's not just about the voltage, torque, and RPM. The application places specific requirements on motor performance beyond these basic specifications. Both motor load and motor speed are important. Depending on the application, a system-level approach may show the machine does not always operate under a constant production rate, demand, or environmental conditions. Looking at the system as a whole may highlight that the motor rarely approaches maximum load or show that reducing motor speed at times is possible to improve efficiency. The current narrative on motor efficiency is to take a system-level approach. It's not just a pump. It's a system with supply and demand sides that interact and affect system performance and efficiency. Oversizing a motor to give it a safety factor may provide plenty of torque for the application, but efficiency just took a hit. To size a motor and drive system to operate more efficiently, run it between half to full load. Optimal efficiency is at approximately 75%. The motor may not be most efficient at loads less than 50%, but if the system works as needed at these loads or motor speeds, it can certainly save energy. Depending on whether the system is a variable or constant torque load, using a VFD to adjust the rotation speed of the motor-driven equipment can save significant energy with small speed changes. The motor load includes a variable or constant torque and a variable or constant horsepower. The motor may also require positional control or torque control. Some loads are constant torque. The load doesn't change. For example, the lever arm or roll diameter remains constant. In some constant torque applications, the horsepower may vary. More work needs to be done or more force is needed to do the work. Basic examples of these constant torque and variable horsepower applications include compressors, cranes, conveyors, and some pumps, gear type or positive displacement. Compressing at a higher air pressure, lifting different weight loads with the crane, or adding a loaded pallet to the conveyor varies the motor horsepower needed to move the load. Define the work. A wide variety of AC and DC motors work well on these applications. There are also constant horsepower and variable torque applications. A simple example of this is an unwind or rewind application. The material speed remains constant while the roll diameter decreases or increases. The constant material speed ensures a constant horsepower while the roll diameter, lever arm, changes, varying the torque. This application commonly used DC motors many decades ago. More recently, servo motors or AC motors with closed-loop control are popular choices. With these heavy loads, don't forget about regenerative braking as a means to control the regenerative power when stopping. There are also variable horsepower and torque applications, such as mixers or agitators, fans, and centrifugal pumps. These are the type of applications where energy efficiency is often discussed. Small changes in the speed of these motors results in large reductions in energy usage. The speed of a motor is always part of the motor selection discussion, as is an application's need for frequent or fast starts and stops. Will the motor need to start and stop or reverse direction often? Does it need to do so quickly? Will the motor run at constant speed, or does it need to be variable? The answers, in addition to determining the type of motor needed, such as an inverter duty AC motor, helps to determine if across-the-line starters or variable frequency drives are needed. More advanced motor applications require accurate and repeatable positional control, torque control, and speed control. These applications include single and multiple axis gantries, pick and place, and web handling machines. While a stepper motor running open loop may satisfy the requirements of these applications, closed loop control using servo motors is often required. Do you really need a servo motor? An AC or DC motor with encoder feedback can also be used in many high-performance applications, providing good speed regulation and reasonable positioning capability. For example, an AC motor specifically designed for inverter or vector duty works well in variable speed applications and can provide constant torque capability to zero speed. DC motors include both brush and brushless types. The brush type, such as permanent magnet, series wound, shunt wound, and compound wound, use internal commutation and are connected directly to a DC power source in order to operate. Brushless DC motors, such as stepper motors, need an electronic drive to operate. The DC motor has many desirable characteristics. A notable one is that it has maximum torque at zero speed. The DC motor is typically simple to install with a wide speed control range, high starting torque, and quick acceleration, stopping and reversing. AC motors include both induction and synchronous types. The induction motor can be run directly from line voltage through a motor starter using a variable frequency drive or a soft start. The synchronous motor's rotation is closely synchronized with the supply current frequency. AC motors offer low power demand when starting, and the acceleration, speed, starting current, and torque limit can be controlled. A servo motor can be many types of motors. Many are DC motors, and brushed DC versions are the simplest of servo motors. However, many of the servo motors used in automation are brushless DC motors. The AC brushless servo motor with permanent magnets is another option that provides higher performance. Drives are closely matched to the motor specified, but there are many types, including variable frequency drives, stepper motor drives, analog servo drives, digital servo drives, brushed or brushless DC drives, and others. Controllers tell the drives where to move the motors that turn the electrical energy they receive into mechanical energy. The motors produce the torque to create the rotational force or linear force when connected to an actuator to rotate at a set point speed or move to a commanded position. Keep in mind that VFD efficiency decreases with decreasing motor load. So a constant torque load running at 25% load will not see the full benefit of running at a reduced load. However, when it comes to variable torque loads, even with reduced motor and drive efficiencies at lower loads and speeds, the energy savings are still impressive. As with all other sectors of automation, the demands for more performance in a smaller package has moved servo and stepper motors into the forefront of automation projects. One of the primary motivations for moving in that direction of servos was the open-loop nature of VFD and stepper control. Some manufacturers have closed the gap between a VFD and a servo drive by producing a variable frequency drive that accepts encoder feedback directly into the drive. Now motion is controlled at the drive level, instead of using the PLC algorithm to approximate closed-loop control. These drives are less costly than a servo drive solution, but are actually controlled using the same commands as a servo. Not to be outdone, some manufacturers of servo drives offer the option to additionally control a VFD from that same servo drive. Further sweetening the pot, today's VFDs also make use of integrated safety features that provide a safe torque off function. With STO, the drive is prevented from producing any torque generating energy. When this feature, a physically wired dual channel connection, is used in conjunction with a safety relay, there is a means by which to guarantee that a motor is disabled when a safety device is tripped. Finally, in what environment will the motor be installed? The motor selected for industrial applications must be robust and capable of handling the environmental conditions. Don't make the mistake of specifying a single-phase AC induction motor, often used on a small appliance such as a washer or dryer, to control small loads on a machine. There are significant differences between a continuously running industrial machine and a washing machine cleaning 6 or 8 loads of laundry a week. The appliance motor may work great, but there is more than just dust present in industrial applications. Motors need to survive extreme environmental conditions, including high and low temperatures, varying electrical demands, and contaminants. A properly selected motor will provide optimal performance and a long service life in harsh environments. Washdown duty stainless steel and severe duty are just a few requirements to consider depending on the industrial environment.
MOVI-C automation solution from SEW-EURODRIVE features a flexible automation platform for a single source, combines fully integrated drive components, control electronics, and automation software, and makes even advanced automation easy. Add MOVI-Kit pre-built software modules for common tasks. It is compatible with Ethernet IP, Profinet, EtherCAT, and other communication standards. Learn more at SEW-EURODRIVE.com. Beckhoff's ELM72 series servo terminals are directly integrated in the standard EtherCAT I/O system. This is a complete servo drive built into an I/O terminal with a robust metal housing and increased output current up to 16 amps at 48 volts DC. Learn more at www.beckhoff.com.